Okay, good. Recently I'm reading two papers of Wheaton. One is random matrix and deformation of JT gravity. And another one is the phase transition JT gravity. Um, both of both of them are not hard to understand. So I need to spend some time to have a knowledge. Yeah, that's okay. Very good. Nice. Okay. We first uh, to see see the paper. I share the screen. Okay, great. Okay, let's us look at the paper. We first see the deformation of jetty gravity and phase transition. Um, Actually, in this paper, we can just discuss the classical phase transition. In particular, he just discussed the phase transition of the black holes. But until to now, I didn't finish reading the paper. I just read half of it. But actually, it's just the classical phase transition. Which means that we assume that we have a black hole solution, and we put the solution into the action and to calculate the free energy. Then we evaluate the minimal value of the free energy. So here the phase transition comes. Okay, but here we consider a general potential for the dilate gravity. Then then we also suppose some other constraint, which means that we impose the potential. Oh no, sorry, the potential have the same asymptotic behavior as phi go to infinity. It should go to like 2 times phi. Okay, so and so on the boundary it looks like the ordinary JT. Okay, this is the condition we need to impose. And now we suppose that we have a general black hole solution for this theory. So we have ds written like this form. Then it's not hard to put the metric back to the action of the Dalton gravity. Then you will find the action can be written like this form. Uh, okay, good. Uh, then or maybe I need to use some. Is there some derivative? Okay, very good, very good. This is some derivative uh, for this paper. Now we start with the boundary condition. Boundary. What is boundary? Why is this boundary? Oh, sorry. The index B means bug, not boundary. Okay. Here, because it's not, we can't impose that R go to 2. Okay, no -2. Any other thing because the potential is general. Then we just think that assume that we have a black solution. Then we put the black solution into the action and write it like this form. Then we can integration by parts, which means you notice that there is a derivative over R. Then it can put back act on phi. So phi become phi prime. Then it's quite easy to study the equation of motion by varying g. So we are using this formula. Okay, you got the first equation of motion. Then you can simplify it by parametrization symmetry. Notice that the metric can be written like this. You can just write it like this. So you just define this one as dr tilde square. So r is a function of r tilde. So here we can just write the new g tilde is the same as a. Okay, so we can simply simplify the action to this form, and in this form we can vary phi to alter a simple. You could we have vary g. Okay, but in this equation there's no g, so you need to just use this equation. In the equation, and impose the condition that g equal to a, then you will simplify the equation to this form. Oh, it's quite simple. Then for this action, we can do IBP so that the second derivative on a can be can be moved to on phi. So it is like this. Then it's quite easy to vary a. Then you got that the second derivative of phi field is equal to, well, phi is just a diatom field equal to 0. So phi should be linear with r. And okay, and we found that the metric is invariant under the symmetry. This is the isometric symmetry, so we can choose a special coordinates to make that phi is just r. Okay, good. And let's see this equation. So now we go back to this equation, not because r equal also phi is equal to r. So phi's prime, phi's derivative is just 1. So it's quite easy to should this should be minus, sorry. This should be minus. I have made a mistake. So a prime is equal to WR. So the solution of a is just integral from the horizon, which means that a h equal to 0. Okay, this is a solution. It is a is given by the integration of w. Great. Okay, this is some derivative. Good. Then let's see. Okay, this is the case. Then we can interpret r equal to RH as a black hole horizon. Okay, and at the horizon, the delta field is just RH. Okay, that's great. Okay, then we can expand the geometry near the horizon, written by this one. That's because you can think that when r is near to RH, so we can write it as a Taylor expansion, or anything you want. Then okay, that's great. Then there is another constraint on AR. I think because we always assume a black hole solution in the Euclidean signature, where we just require that AR is positive for any R out of the horizon, which means this one, for any phi larger than phi h, this one should be positive. This is the constraint. Anyway, then you can see the new variable y is near the horizon. Then you can write the metric near the horizon like this formula. Okay, for this formula, you can interpret y as the radius, and t as you can interpret it as an angle, because we are working in the Euclidean signature. Then you will find this one should have a period of 2 pi, so which means t has a temperature, have a period of this, and in Euclidean the time t is actually the tau. Okay, so it gives the temperature. It's a temperature, or you can calculate it by the Hawkins formula, but it's not so hard. Anyway, you know that the temperature near the of the black hole, which means at the horizon, is equal to the potential at horizon. Okay, that's great. Then we can see that as explained in the introduction, we want W has the same asymptotic behavior as pure JT. So we may assume this behavior. Then you can write AR like this formula. Then anyway, finally we can obtain the energy for the black hole and the entropy for the black hole. Maybe we need to jump to the derivative. Good. We have assumed that for a large R, the WR has the asymptotic behavior. Okay, this one is subneeding, quite subneeding. Okay, it's not a constant. It's quite subneeding. Go to 0. Okay, that's great. Epsilon. Okay, it's quite. So then you can write AR. AR is what? It is an integral for W from RH to R. Okay, then you can put the asymptotic behavior into it. It just holds for the large R. So this one is right, but this one collects the behavior of small r. Okay, and other things. Okay, so all the behavior of the small r is captured in B. Okay, sorry, and you need to think that AR is also a function of RH. Okay, this thing is not a constant, but a variable. You need to think that. So then we take a derivative on both sides. So we can say that dA is equal to what? Equal to from this part is equal to 2r times dr and minus dB. Okay, that's great. Okay, good. Times this one. Cool. And from its integration version, we have the variation comes from the start point and an end point. So we have this formula. Okay, then we take r go to infinity. This is the limit we can take. Then we find these two terms cancel with each other, and the high order term can be neglected. So we will got an equation at dB equal to W phi h equal dh. Okay, this equation. And we notice that beta can be written in this formula. So we can find that dB is equal to T times D phi h. Okay, very good. It is quite similar to the black to the thermodynamics of the black hole, which means that dE equal to TdS. Okay, that's great. So you want to interpret the parameter B as the energy of the black hole. Okay, this is what we want to do. Now we need to derive it. It's quite straightforward. You just put back. You just put back the solution into the action. That's because on the classical level, the partition function is just equal to the free energy. Sorry, its logarithm it should be equal to the free energy. Okay, then you can compare the expression you got for the free energy to its definition. Its definition for the free energy F is equal to T minus E minus Ts. Okay, and you will obtain the expression for T, so for energy and entropy. This is the whole story. Okay, let's try to derive it. We have the boundary action. Let me see. It's a boundary action. Okay, you can just write it. Then you calculated the external, sorry, the external curvature H. It is just AR infinity and sorry, this is the metric, sorry. This is the curvature, extreme curvature. Not extreme curvature, external curvature. Okay, and you put everything down into it. Okay, good. Then what can you get? The datum field is just R infinity, so you times here, and this one here, and all of this thing is independent of of tau. So the integration of tau just gives beta. Okay, that's great. This one is the boundary. Okay, all is from this one. Then you just take the you just plug in the asymptotic behavior of A inflated into this formula. Then you can just drop some other high order term, and you got this one. This is A, the derivative of A, so it is equal to 2 R inflated, and you can find it. Notice that it is a square, so you can just open it by the Taylor expansion, and you finally got this formula. Okay, good. Then we consider the bulk action. For the bulk action, we can firstly write this Oringer formula, that it is what? Let me see. Why is A prime plus W? What is? Oh, okay. Oh, what is? The bulk action should be something like, it should be curvature. Okay, curvature plus the potential. Okay. Great. Anyway, you can find it. Then you put everything in it. Then you just take R inflated to inflated, then you will get this equation. Good. Then maybe you can plus some topological term. It gives minus S0. Note this formula. This is the action. The action of the partition function in your Euclidean signature is just equal to the free energy. The free energy is beta T. Sorry. It is another factor. It's beta. Okay, it's beta T, beta E minus S. Now you can read out the expression for the energy. Yes, it's actually equal to 1/2 of B, and the entropy is proportional to the diatom field near the horizon. Actually, it's just proportional to the radius of the horizon. Okay. Yes, because phi h is just RH. Okay, this is all the story. We'll go back to it. Very nice. Maybe what I need to do. Okay, good. Good. Yes, this is some basic thermodynamic formula. Dynamic formula. Then here will come to some discussion for the phi h. The phi h is interpreted as the horizon of the black hole, and S is the entropy. We know that the entropy for a thermodynamic system should be bounded below. Okay, and it is proportional to the position of the horizon. And what is the horizon? Yeah, fetch. How to determine the horizon? Okay, it should be determined by the constraint of A, which means that the horizon is the minimal value, or the minimum value which satisfies this equation for any phi which are larger than the horizon. Okay, this is definition of the horizon. Okay, you need to find the minimal value of phi h. Okay, and then we require that the minimal phi of phi h is not equal to minus infinity, because the entropy should be bound below. Okay, this is the case. Then you will solve some discussion. Maybe I need to record another video, because here I need to plot some figures to show the idea of this equation. Anyway, you can just plot the figure for W phi. Okay, then you study, you just assume that, okay, that we have assumed the phi zero is a position, a candidate position for the black hole's horizon. Then we found what is. You will find and one important conclusion is that at first we need to know that WH phi h should be positive, okay? Because we will study that from phi h to, we have an integration from phi h to another, any point should be positive. So phi h must be positive. Okay, this is the first case. Then we study the stability of the thermodynamic system. Stability means that the energy should, the derivative of energy over temperature should be positive. This is a condition we need to impose, which means that then you drop WH, then you assume that we want to find the black hole horizon. The derivative of WH should be positive. If it's negative, it is not thermodynamic stable. Okay, it's a case, and then we have many stable point. Okay, but actually the thermodynamics physics will choose a global minimum of it. Okay, then there comes another discussion. Okay. Okay, I think I need to spend more time on this paper, but actually I think it's just quite a classical discussion of the phase transition. Okay, this is nothing more than our message. Okay, our knowledge about the physics. Yes, good, nice. Okay, maybe what's the time? I need to have a lunch. Okay, let's end it.